Hello, Tensor friends. I was playing around here with Desmos, desmos.com/geometry. It's their geometry tool. And I was able to do a simple, the tensor calculus, the problem, and graph it at the same time. So it's kind of fun. I wanted to show you. Now, I had to type all this out ahead of time because I typed so slowly. Believe me, you don't want to watch the sausage being made. It's just, it's horrible. Okay, so we make up a point here. Okay, we can move that point around. Here's its components, the P1 and P2, uh, and we want to take that point and align the segment from that point to the origin. All right, so it looks like this. Now we want to work in plane polar the coordinates, so we're going to need a radius. Okay, so this blue line, the segment defines the radius of a circle. All right, so now this blue, the segment also defines an angle from the x-axis, and we can show that as well. So there is the angle, and it's changing. So now we have the two components that we need, the coordinates for polar, the coordinates. We have r and we have theta, this angle, right? And r, we need the magnitude of that, which is given by this, just the Pythagorean, the theorem. So it's this distance squared plus that distance squared equals that distance squared. So we take the square root of those, we get our magnitude of this, excuse me, this line's the segment, which is the radius. All right, so let's get rid of that circle because we don't need it. Now, what we want to do is define basis of vectors in the coordinates. So the way we would do that is we would write a vector capital R, right, is made up of its components and basis of vectors, and its components, we want them as a function of r and theta. So if you look at this, the x component, if this blue thing is now a vector r, the capital R, the components of that are, this is the x component, so it'd be the cosine of this angle would be this divided by the hypotenuse. The sine of this angle would be this divided by the hypotenuse, so we can write this equation. R, the radius, times the cosine of that angle, times this basis vector, plus r, times the sine of that angle, times that basis the vector. Now, to get the basis vectors in polar, the coordinates, we take the derivative of a position vector with respect to a coordinate. And this coordinate is a function of r and theta, right? R and theta. And if you're wondering why I'm not using the theta and x's and y's and all that, because Desmos is very picky about x, y, r, and theta. You got to be real careful how you use them because they hold them for special the purposes. So you have to make up other names like that's A1, anyway, it works. So what we're going to do, because this is a function of r and theta, we have to take partial derivatives, right? So the partial derivative of this position vector r with respect to r is, this is a constant, the cosine of the angle is a constant, and derivative of r is 1. The derivative of this with respect to r, this is a constant, derivative of r with respect to 1. So we get this. Now, if we do the same thing with respect to theta, r becomes a constant. We write that down. Derivative of cosine is a minus sine. The same thing here. We write down r. Derivative of sine is cosine of our angle. All right. Now, let's move this out so we can see it. Is it? Yeah, that's all right. All right, so we want to put that in a vector, the form in Desmos. So we say the ER basis of vector. Now this is the covariant basis of vector in polar the coordinates, right? So we want to start it at point P, because if you try to define basis vectors at the origin, it doesn't make any sense in polar the coordinates because you need some R and you need some angles. So defining it here makes no sense. So we start it at P. So we're going to have the x component, if you will, is cosine of the angle. And now we want to add that to the point P1 because we want it to be here and in this direction, wherever that is. And this component is the sine of the angle plus the P2. So we can see this is now the ER basis, the vector. And the first thing you know, as you change the angle, it changes direction. But as you change the radius, it doesn't change length because it is a unit vector. It turns out it's a length 1. Do you see that? So it's the same length everywhere, but it changes direction. Changes direction. All right, now let's do E theta. So E theta is the same thing. We start at P. We take this component, we add it to that basis vector, to that point, the P1. We use this component, we add it to that, the point, the P2. So this is our E theta basis vector. So we've got E theta and ER, and you notice they're orthogonal. They're 90 degrees apart. Now watch this E theta. It changes not only direction when you change, but it changes length, right? So at a constant radius, if I could do that, the length will be the same, but the direction will change. But it all changes length as you change R, okay? And it turns out that it is the length of R. You see that? So this is whatever that is, 1 something. It's the same length. All right. So we've got E theta, we got ER and E theta. Now these are covariant basis vectors, right? We want to find contravariant basis vectors also. Well, how do we do that? Well, if you remember, if you multiply, the way you raise and lower indices in tensor calculus is you multiply whatever you're interested in changing by the metric, the tensor. Well, we've got 2 basis vectors, so we can find a metric, the tensor, right? The metric tensor is defined as the product of the basis vectors. Well, ER.ER is just 1, and we knew that because it's 1 unit long. And E theta is that number, and that number is variable. You can see it changes wherever we change, okay? Now, whoa, dude, what'd you do? The cross terms here, so there should be 4 components because we got 2 dimensions. So there should be a GRT, the T stands for theta, and a GTR. Well, there's 0. The reason being why? Because this is orthogonal. And remember the product is the magnitude of this times the magnitude of that times the cosine of the angle between them. Well, the angle between them is 90 and the cosine of 90 is 0. So all the cross terms are 0. So we have our metric tensor. So finding our inverse metric tensor is really easy. It's just the inverse of these 2 numbers, right? That's not always the case, but in this case, it's very, very easy. Now, DESMOS will not let you do superscripts as indices. When you do a superscript in DESMOS, it's an exponent. So you just have to make up some other new the numbers. So E3 is actually the contravariant basis vector ER. So this should be E, the super R. It won't let me do that. So the way we raise this index is multiply it by the metric, the tensor components. Now this is actually multiplied by 2 components, so it should be plus 1 over GRT, but they're all 0, so no point in me writing them out, right? So if we plot that, you see that red guy turn blue? So the ER and E theta basis, the ER contravariant and ER covariant basis vectors are the same, okay? Now, so E4 is the contravariant basis of vector E, so it should be E super T. It should be E super T. And we find that by multiplying the covariant basis vector E theta times the inverse metric, the tensor, and it looks like this. Now, it is not the same as its covariant the basis to vector. You see that as you get closer to the origin, it increases length, and as you get further away, it decreases length. But it changes, it goes in the same direction as E theta, but its length varies. And it does that because they're orthogonal. This isn't orthogonal, the system, even though it's curvilinear, it's orthogonal. So that's why they're on top of each other. So I thought that was fun that you could show an entire calculation here. I don't know that uh, DESMOS is capable of doing partial derivatives. I certainly haven't found it out, but these were so easy. We could do these in our heads. And it did the metric tensor and did the inverse metric tensor, and we got this fun little graph to play with. Anyway, I thought that was fun. I'll see you later.